Good morning, or good afternoon, or good evening, depending on when you're listening to this. This is Dr. John giving the first lecture in the physics class for 2016-2017. I want to welcome you to this class. This introductory lecture is on the mathematics of physics. And what I want to do is go over the principles of how we do problems in physics and focusing on a couple of ideas that are important and will be important throughout your time in this class. One of those principles is the whole idea of units and how we work with units. The second is the idea or the distinction between accuracy and precision, and related to that is the idea of significant figures and how significant figures give an indication of the precision of a measurement and a result to a problem. And then finish up with a brief discussion of approximation. I thought this scripture was interesting. Actually, it's meant to be a joke, but it says, "It is good for me that I have been afflicted, that I might learn thy statutes." Many people see physics as an affliction. However, it is good that sometimes we are afflicted with these sorts of challenges, that we might learn the way God operates his universe. First of all, we have to start out with some definitions in the area of units and working with units. We apply units to various situations, and in order to do that, we have to understand what these situations are. The first of these is something we will work with from time to time, known as a model. You need to understand that when I talk about a model in class, I'm talking about a schematic representation of a process that is many times too difficult to demonstrate or display in real life. The important thing to understand about a model is it's artificial. It's not the way things really are. The problem is we probably don't know exactly how things really are. But in order to understand and put together the information we do know, sometimes we have to make up a representation of that process so that we can understand it. And it's important also to understand that we do this because otherwise we would not be able to do the demonstration or to display what we want to say. Now, this is in distinction to a theory. In a theory, what we do is we put together the information that we know based on observation and experimentation, and we put together an explanation for the patterns in nature that we see that are supported by the scientific evidence. And it's important to understand that for a theory to be accepted in science, it's generally been verified many times in various different groups and with various different research institutions. So you need to understand that when you say something is a theory, you're not in some way saying that it's unstable or that it's a possibility. It's a probability. Now, it's still falsifiable. Dr. Popp, who is a famous philosopher of science, defines science as a process that is falsifiable. That means that it's possible to find evidence that will falsify whatever you believe. And a theory is falsifiable, but it does not mean that it's not probably true. The reason I'm emphasizing this is many times people talk about the theory of evolution and think because it's called a theory, that means it's not well supported. That nothing could be farther from the truth. They also talk about the theory of relativity, and virtually all scientists believe that relativity is true. So I strongly recommend not getting into that argument where you say, well, it's only a theory. A theory is is supported by a very strong amount of evidence in general. Now, on the other hand, a law is something that is a concise description, generally and many times using mathematical formulas, for a pattern in nature that has been shown in repeated experiments. So, for example, the law of gravity has been shown to occur over and over and over and over again. Now, I am not going to get into the problems of induction, but again, even with a law, it is possible to falsify a law. And so both theories and laws can be falsified and can be questioned. Most of Newton's laws relative to space and time, etc., have been generally falsified by the laws that have been generated through the theory of relativity. And so even those laws that seem to be fairly stable, they can be falsified. And even laws that have been falsified, such as many of Newton's laws, are still used because they explain 99.99% of the things that happen in our universe, and are only falsified at very extreme circumstances. So here's an example of a model. This is the planetary model of an atom, and generally this was generated to help people understand the information that we knew about atoms, electrons and protons and neutrons. It's a mental image of an atom. We cannot see an atom directly, and it shows the nucleus as the center and the electrons as flying around, like orbiting the nucleus, much like the sun being in the center and the planets rotating around the sun, or a planet being the sun center and the moons around that planet being those particles that fly around the outside. So this is an example of a model. Models are very useful, but cannot be taken as the absolute gospel truth, because remember, they are artificial generations based on the data that we have. Now, I cannot overemphasize what I'm getting ready to talk about in terms of units. It is extraordinarily important for people to understand what units are and how to use units. And again, we have to start with some definitions. The units that have been accepted worldwide are known as SI units. Now, SI stands for System International. The System International was developed in order to standardize units across the world. As you probably well know, there are various unit systems out there. And in order to try to standardize units, the Systems International was developed. The 6 fundamental units of the System International are shown in this slide: the meter, the kilogram, the second, the liter, the ampere, and the candela. All of these measure different aspects of the universe. The meter is length, the kilogram is mass, the second is time, the liter is volume, the ampere is current, electrical current, and the candela is light intensity. Fundamental units are basic. In other words, they're not derived, and we'll talk about what the difference between fundamental and derived units here in just a moment. The English unit system is the unit system in Britain and the US. The metric unit system is generally used in the remainder of the world. The SI unit system is foundationally based on the metric system. The US, as you can see, the same 6 parameters in the U.S. or English system are shown here, and you can see there is some of those units that are the same and then others that are different. Now, derived units are units that are produced by a combination of fundamental units. For example, the acceleration, which is the increase in velocity divided by the time it takes to increase the velocity, and then velocity being the distance covered over time. So if we start with velocity, that's a derived unit, and it's a length divided by time. So it's meters per second or yards per second. And then acceleration is velocity over a period of time, so then it becomes meters per second or meters per second squared. And then we get to the units that I've shown here, the Newton being the mass times acceleration, a unit of force. And its mass kilograms times meters per second squared, or the Joule, which is force over distance, so it's kilograms, so mass times meters, distance times acceleration, meters per second squared. So the derived units are all derived from fundamental units, are all produced from fundamental units. Now this last statement is the most important statement that I'll make about units. Always label your answer with units. I will take off if answers are given on quizzes or tests or homework that do not have units. So it is extremely important, because an answer without units is useless, as this next slide shows. In this case, a unit has been given, but the poor observer here doesn't know what it means. He's thinking, what's a cable? Or how long is a cable? So in order for this to be useful, you have to have some sort of way of translating cable into meters, which is the System International unit for length. So distance given in unknown units is maddeningly useless. A distance given without units is even more maddeningly useless. Now, fundamental units have very specific and interesting definitions. For example, the meter is defined as the distance light travels in a very short period of time, shown on this slide, in a vacuum, because the speed of light is mildly different in a vacuum versus in other media. This distance then can be multiplied by time in order to show the velocity, or to come back to the velocity of light. So what you see here is a very fundamental definition of a fundamental unit. They define a second in terms of the oscillation or the vibration of a specific atom in a specific environment. And so these fundamental units have very specific objective definitions.